Hello everyone, my name is Puya Taheri. In this presentation, a summary of the paper submitted to the IEEE Syscon 2020 titled A Mathematical Model for Combined Workforce and Vehicle Route Planning Within a Time Window, authored by Amin Taheri, Vahid Reza Ghazavati, Asal Guderzi, and myself, is presented. Workforce planning helps organizations understand the status, surplus, and slack of their human resources. This understanding helps assign workforce efficiently to the appropriate work with minimal cost. This also ensures compliance with safety and labor laws. Therefore, a comprehensive model is needed to cover all the elements of workforce planning. The presented model in this paper can be applied to the transportation industry, such as airlines, railways, and any urban transportation system in which the assignment of workforce to vehicles and vehicle route planning are considered. Vehicle routing is an optimization problem in which the customers are served by vehicles that depart and return to base depots. In this problem, the number of depots and demands are known, and each customer is usually served only once by vehicles. However, in our study of the combined workforce and vehicle routing problem, each customer can be served by different work teams. Meta-heuristic approaches can present feasible, non-optimized solution within a reasonable time frame for large problems. This study proposes a mathematical method to plan workforce within a time window in vehicle routing problems based on Tabu Search and variable neighborhood search algorithms. Numerical solutions and sensitivity analysis are presented to show the validity of the proposed method. The method proposed in this work assumes that each customer has a certain number of tasks that can be done by different specialized teams, and post requirements of each task and corresponding restrictions along with the set time window are assumed predetermined. Early or late arrival outside the time window lead to delays and penalties. In our work, we have made some assumptions, including that the number of work stages, vehicles, and demands are known. Teams' work time are known. The travel duration between customers is also known, and the time of serving services are based on customers' time windows. A model sample is shown in this slide where you can see the base depot, number of vehicles, number of teams and work stages, also time windows and route planning configuration. This model's objective function covers minimizing empty vehicle movement, early or late arrivals, the number and duration of trips to transport a team, delays in finishing services, and delays in returning to work after breaks or vacations. We have also considered a weighting parameter in the objective function that is used to prioritize different objectives. In small-scale problems, this parameter is usually set to 1. The objective function's mathematical expression is provided in this slide. Some of the model's constraints include start and finish depot are the same. Vehicles numbers in arrival and departures are consistent and balanced. The early serving, delays in serving, the time of being ready after breaks or vacations, and delays in starting vacations are all considered and calculated. The model proposed in this work tackles the workforce allocation problem within time windows, job teaming constraints, and a limited number of teams. Mathematical constraints assumed in this paper and shown in this slide guarantee that the start and end points are the same, the number of incoming and outgoing vehicles are consistent and balanced, customers are served for every task, preparation time for a task is not earlier than the task's end time. Also, the early or late arrival time, preparation time, and delays after breaks or vacations are calculated and considered. Tabu search algorithm is an effective method in optimum route planning. This algorithm starts the solution from one point, then searches through the neighboring points to find the optimum solution. This search continues until the stopping criteria are met. In this algorithm, a random initial point is generated. Then the method starts for searching among neighbors with better values. Visited points are put in a taboo list in order to prevent search loops. The problem with this algorithm is potential convergence to the local optimum point instead of the global one. Variable neighborhood search is a meta-heuristic optimization method that explores distant neighbors and moves from there to a new one if and only if an improvement is made. The search is done repeatedly and iteratively to find the optimum point. In order to prevent the trap of local optimum points, the proposed method in this paper combines Tabu search and variable neighborhood search to solve the problem of workforce allocation and vehicle route planning within a time window. In this method, the systematic replacement in the structure of neighbors avoid the trap of local optimum points. The pseudocode for variable neighborhood search is provided in this slide. In our proposed solution, the answer is modeled as a matrix with 3 rows. The first row represents visited customers in the route, while the second and third rows represent team numbers and work steps. We combine Tabu search and variable neighborhood search algorithms to improve the results, and the results are verified with those obtained from a commercial software package called GAMS. A sensitivity analysis is also provided for number of vehicles, teams, and tasks. As shown in the flowchart in this slide, 100 initial answers are randomly generated, and the best one is selected. This initial filtering results in a final answer with higher accuracy. The best solution is then found based on an iterative try and error method. To verify the performance of the proposed algorithm, several examples are generated using MATLAB based on random data with normal distribution. These examples are simulated using the proposed method and are compared against the result obtained from GAMS software package. Tables in this slide present the simulation result for the studied examples. The computation time for different examples using GAMS and the presented method are compared in the shown figure. It can be observed here that accurate results are derived while the computation time was significantly reduced. A sensitivity analysis based on 3 parameters, which is number of vehicles, teams, and tasks, is performed, and the results are provided in this slide. According to the sensitivity analysis, it is concluded that increasing the number of vehicles reduces the value of objective function up to a saturation point. Also, increasing the number of teams reduces some cost while increasing other costs, and optimum number of teams can be calculated by minimizing the objective function. Another conclusion is that increasing the number of tasks increases the cost in a linear trend. In this work, the authors studied workforce planning for the vehicle route planning problem within a time window. The methodology and formulation were presented, and the proposed method was verified using randomly generated cases versus GAMS. Accurate results were observed while the computation time was reduced significantly. A sensitivity analysis was also performed to study the effect of number of vehicles, teams, and tasks. This proposed method considers stages of work, time windows for each customer, early or late arrivals of teams, and return to work delays. This work can be utilized in airlines, city trains, and municipal transportation centers where human resource allocation should be aligned with vehicle planning. Thank you so much.